Hello class, this is your TA, Gilberto Fonseca. Today I will be talking about the Fischer esterification of acetic acid with isoamyl alcohol. This is a variation of exercise 30.2a from your textbook. You should consult with chapter 30, but the primary procedural modifications are in this lecture. In this experiment, you will be synthesizing an ester, isopentyl acetate. So this is isopentyl acetate, that's 3 carbons, 1, 2, 3, and then that's the 4th one, and then the 5th one, and then this is your ester. So you have an O there, and then another carbon, and then carbonyl, and so it actually is a methyl ester. So this portion of the molecule is the methyl, this portion is the ester, and then this portion is the isopentyl, right? 1, 2, 3, 4, 5 carbons. So again, 1, 2, 3, 4, 5 carbons. That's the isopentyl. This is the ester. Ester is a ketone with a oxygen attached to the carbon, and then this final methyl. So it's a methyl ester, right? It is often referred to as banana oil because it smells like a banana. The reaction that we'll be conducting is called the Fischer esterification. It's an equilibrium reaction, and it's usually not far shifted either toward reactants or products. So since it doesn't favor the quantitative 100% formation of the ester, we use Le Chatelier's principle from General Chem to shift to the right in favor of the product, and we do that through adding an excess of acetic acid, which is the cheaper reagent. We also use sulfuric acid, H2SO4, which helps bind the H2O produced. So the synthesis of isopentyl acetate is an isolation procedure. In this process, much of the excess acetic acid and the remaining isopentyl alcohol are removed by extraction with sodium bicarbonate and water. Just another example of how extraction is very important. I would say it's as important as the reaction. Whatever we do afterwards, the washing is as important. So after drying with anhydrous sodium sulfate, the ester is purified by distillation. So the purity of the liquid product is then analyzed by higher spectrum or NMR or mass spectrometry. So this is an example of an esterification, but this is between acetic acid and ethanol. So it's the real reaction that we will perform is similar. So you have acetic acid, and you have a proton, and those electrons want to hang around the very positive proton, and so they'll attack and they'll steal it. So then you have this diol, but the formal charge of that carbon is positive, and it'll tautomerize to this other structure, and in comes ethanol, and since it has a very negative region here, it essentially becomes a nucleophile. So then it's going to attack the carbon, the positive carbon, and it's going to become this structure. The formal charge of this oxygen is 1, again because you have 1 bond, 2, and 3, and so it's not drawn, but there's supposed to be 2 electrons here. So then 1, 2, 3 plus those 2, you have 5, and 6 minus 5 gives plus 1, the formal charge of, in this case. And that's important to note because you'll have this transformation over here where these the electrons from this bond are going to want to stick around and balance the formal charge of this oxygen to make water. Again, this is a good Levin group as it is already. So then you're gonna have water leave out as is, and you're going to have the ethanol attached to that positive carbon, this original carbon, um, through a ketone structure here. That then an additional hydrogen is going to leave. This initial hydrogen that came in is going to leave finally. So it's going to catalyze. It's essentially catalyzed by an acid, which is what I mentioned earlier with sulfuric acid. So this proton helps this water leave through this structure, right? So if there wasn't this proton, this water wouldn't be able to leave, and that's important to note. So now the actual reaction that we'll perform is a little convoluted, but we'll get through it. So you have isopentyl alcohol, this structure over here, and you have acetic acid. And then, with the help of that acid, of sulfuric acid, this carbonyl, the electrons from this carbonyl, are going to grab onto it, and then this structure, the isopentyl alcohol, again, this is highly negative region, is going to attack the changing. So these two structures are interchangeable, right? This one is going to attack here, and it's going to start making that ester, that base skeleton structure. So then, once you get to this area, jump back here, you're going to have that proton, that region, or that environment that is highly acidic is going to add another proton. And this, as you can see, is easy to leave. It's a good leaving group. And so now that water molecule leaves, minus H2O. And so you're going to end up with a structure like this. And again, you have a positive carbocation, and you can have some rearrangement. So this proton is going to want to leave because the electrons from that bond want to hang around this positive area, which is noted here. So now you have that formation of the final carbonyl, and right, this proton is going to leave as well and reform the sulfuric acid. So Le Chatelier's principle. This is what we're doing. So we're adding more of this, of the acetic acid. Although you could also add more of this, and what that is going to do is going to push the equilibrium forward. It's going to make the reaction create more of the products. You could also try to remove water, and that would also shift equilibrium forward. Generally, if the ester is volatile, the best approach is to distill out the ester while the reaction is underway. So if you remove this one, it should have a lower boiling point than water. So therefore, it's easier to remove this one. Then you remove it by distillation, and the reaction wants to proceed to make more. Think about it as it's getting stuck, right? And it prohibits the movement forward. Alternatively, one can add an excess of the cheapest starting compound. But in this activity, we add excess acetic acid and also add H2SO4, which, like I said, is kind of like a catalyst. The effect of H2SO4 serves as a stronger acid to catalyze the reaction. Essentially makes the reaction go faster, and it has strong attraction to water. Helps shift the reaction to the right by binding strongly to the water produced in the reaction. So every time it's produced, it's like you're removing it. So then again, it also drives the equilibrium forward. The equilibrium for these reactions far to the right, helping to shift the equilibrium for the Fischer esterification to the right as well. So as you might know, acids react with water, sometimes violently, and generate this reaction. So the variation, in the textbook they use butanol, but we're using isoamyl alcohol or the isopentyl form, and we also are changing the values of it. We generally follow the textbook procedure, but we use the amount that is shown here. Okay, so this is the reflux assembly. So it's very important to not cover this area, just because you might build a lot of pressure and the column might break. But as you can see, this is essentially the same as we use with distillation. We want whatever liquid is here to not actually leave. So whenever it starts evaporating, this water is going to cool it down. The water coming in and out is going to cool that vapor down, and the liquid is going to condense. That's why it's called a condenser, right? And it's going to drop down. So to a 25 ml round bottom flask, you add in this order. You first add the isoamyl alcohol. If you were working with a solvent, which in this case the acetic acid is the solvent per se, you would usually add the solvent first. But these can be interchangeable. But then you add the sulfuric acid, and that's usually going to start things off. And then you add the boiling chips, and then now you will logically put the condenser on, so that you don't no longer have to add anything else, right? So then you heat. Remember to be careful with H2SO4 and acetic acid. Weighing small masses is usually more accurate. That is true. It might be more accurate to weigh out 2.64 grams of the alcohol directly into the round bottom flask, but it's of course not that easy to do. So you have to make sure that you get the right volumes and the right masses. Also, keep in mind that if the flask that you're weighing on is too big, it might create more variations with your measurements. So if you are going to do this, try to keep the round bottom flask or the Erlenmeyer flask low. Now for measuring the sulfuric acid, remember that 1 drop of liquid is usually close to 0.05 milliliters. Usually with pipettes, with the bulb pipettes, they're usually 1 milliliter. So you can do like half of that pipette, right? So since you need 0.4, you could add 8 drops instead of trying to measure in the available volumetric glassware, which is very small. Sometimes you'll use like a syringe, which measures out every by microliters, so you can use that as well if you have that available. After reflux, you cool the contents in an ice bath because you have acid, and then you wash with water. You decant it from the boiling chips into a separatory funnel. You're going to perform the extraction. You have water. You could add it previously or add it afterwards. And you shake gently because you don't want an emulsion. So an emulsion is when you don't get these nice 2 layers, you get just one thing mixed in with all the contents. So you just drop it and you rock back and forth the separatory funnel, and you allow the layers to form, and you remove the aqueous layer. So the aqueous one should be the one on the bottom in this case. Then you wash with sodium carbonate, and this is done to neutralize your acid. Sodium carbonate, it's a relatively weak base, and that's a recommendation whenever you want to neutralize a strong acid. Use a weaker base, and that's safer usually. You want to swirl the funnel for several minutes and allow most of the CO2 to escape. You're gonna see foaming once you add the sodium carbonate because it's reacting with the acid. And then you cap the funnel and you shake. And when you shake, you want to have this end up, so then you can open it, and release the pressure. Then you allow the layers to form, and you remove the lower aqueous layer. Now you want to dry after the washing, and again you might want to wash several times. If you are really dedicated to this, doing it several times is way better, and it's also more efficient for your reaction because you might wash it more efficiently, right? You may have a small amount of product, but you may want to use a test tube instead of a beaker for drying, because if it's too little, then it's going to be hard to get it out of there, of a bigger beaker. Also, pentane is extremely volatile, so you have to close the source bottle or flask after getting what you need. So you transfer the organic layer to the beaker with a small amount of magnesium sulfate or whatever drying agent you have, and then you swirl. You allow the drying agent to settle, and then decant into a filter to make sure that you're not taking any of the magnesium sulfate. To minimize losses, you rinse this beaker with pentane, which is now your organic solvent, and then you swirl. You allow again allowing the drying agent to settle, and then decant again into the filter. Sometimes you also run down the solvent here to make sure that you get out all of your product. This is the setup for a simple distillation. So you want to get rid of that pentane that you used to make sure that you obtained all of your product. And as you can see, they're very, very different. So it should be easy to get the pentane out. So then you just perform distillation. So that's it from me. I hope you learned something, and thank you very much.